So let's go ahead and dive into it at this point. We've had some more people file in and everything else. I think now's a fantastic time for it. So we do have a lab that goes along with this stuff, but I will talk about that as we get a little bit further into it. For now, let's pick up where we left off last time, right? Talking about how do things actually orbit around. You have hopefully done a little bit more reading on this, and you can see what's going on with a lot of these elliptical orbits as we would have them. We got a couple different things going on, right? Remember last time when we were talking about gravity that we said, okay, even though we're used to seeing mg everywhere, when we take the actual gravity equation, g mm over r squared, and we find an energy with that, it is still a conserved quantity. We can still call gravity a potential energy because despite the fact it's no longer a constant force, it is still a conservative force. That is, it doesn't change the amount of work done depending on the path. I can move a planet anywhere around I want relative to some star, and at the end of the day, when I put it back, it will have had the exact same amount of force acting on it as when I started. It will have the exact same amount of potential energy as when I started. It is completely path independent. So, with all of that, we can say then that at any point throughout the entire orbit, the energy should be conserved. A combination of kinetic energy and of gravitational potential energy. So we can use this to essentially relate, if we know what some sort of orbit is going to look like, we can take every single point along that orbit and find the velocity of that planet as it's going through the orbit, right? Or if we see how fast a planet is moving, then we can extrapolate a lot of information about what is going on with its orbit size, right? Where is it at relative to the star at different points along that orbit? Both of these details might be very useful when we are observing very, very distant things with the James Webb Telescope, looking way out into space because most of the time we can't see necessarily individual planets, but what we can see is a little tiny dark spot that passes in front of a star. And when we see a little tiny dark spot that passes in front of a star, that tells us that that's supposed to be a planet orbiting around. And if we can figure out what the speed of that planet is, we can extrapolate a lot of information about where the planet's at, how fast it's orbiting, what its orbit looks like, all of those details. There's a lot of clever people that can find out a lot of information from just a really, really, really tiny picture, right? Or rather a tiny video watching this thing process across a star. So, energy still conserved. Gravity still works. And if you have done the reading at this point, you'll have seen that we even talk about that as a flat Earth approximation, what we have been doing the entire time with mg. And we say, okay, that's all good as long as you're close. But by the time you are looking at, wildly changing distances, when that gmm over r squared, when r squared is starting to change a lot one way or the other, that's when we have to start considering the actual gravitational force, and we can't just do the mg thing anymore. Even if last time we looked at planet Z and we were just talking about, 10 meters off of planet Z, we drop a ball from the third story, any of those things, mg still would have worked totally fine. We don't have to just be on Earth. It's just we can't be changing r that much. If we start changing r a whole lot, then we have to actually deal with the fact that gravity is a, long-range force here, inverse square. So keep that in mind. But of course, as we're talking about all of these things, we have been doing this sequence over and over and over again at this point. We start with energy, we move to talking about momentum. Now this one I think is a little bit less intuitive. It's not quite as easy to see, but what I'm going to try and say here is that the angular momentum of a planet is conserved. Now, the translational momentum, no. Right? Tangential momentum, as we're talking about it like that is not going to be quite conserved in the exact same way. Largely speaking, because the planet has the same mass the entire time, but if it's going through an ellipse, then it's going to speed up when it's closest to the star. And because of that, the tangential momentum is not going to be the same. And that's a hint for some of these things as we're talking about them, right? The speed increases, but the angular momentum should be. And all we have to really do here is we can look at this in a couple different ways. For one, we can be looking at what torque is gravity going to be applying this entire time. So, M and M, that gravitational force always pulls between the two of them. there is no torque from that piece right there. If we're looking at some of these different sections, angular momentum is going to be conserved as a matter of fact that there is never going to be any sort of torque acting on this thing. It might be speeding up, and that's all right, right? Again, that doesn't actually matter. Even the angular speed is not conserved. It does not go around at the exact same time. It spends a lot less time in this section than it does in this big loop. Not only does it pass through very quickly at a very rapid speed, but it also doesn't spend a lot of time here. Whereas on the very far outside, that's where we've got a lot more time to stand essentially out in this larger loop section of our orbit. But what goes along with that is the fact that even if our angular speed is not constant, the radius is changing along with it. So through this entire step, anytime we're looking at this, even though we are slowing down, we are going out to a greater moment of inertia relative to our pivot point, that star, and angular momentum will be conserved anyways. Do we all agree? Do we feel all right with that description? I can try and explain it again. Is there any spot that I can emphasize a little bit better? Because that might be the play here. If there's one particular spot that I can emphasize a little bit better that perhaps I didn't use the right words for it. Having no torque but changing angular speed. So that is all fine. What we're looking at here is we're essentially trying to look at what's going on with the having these quantities. Think about what direction the radius points, right? R always points from my rotational axis out to the mass. So R points like this. If R points like that, and gravity points back right towards it, if this was a dot product, that would be a maximized negative quantity. But since we're dealing with a cross product, we could also write this out as R f of g sine, and this would be sine of 180 degrees, and it doesn't matter even if it is 180 degrees, sine of 180 degrees is 0. And because of that angle between the two, no matter where we are at, even if we're way over here, the radius, the gravitational force still point towards each other. The angle between them is always 180 degrees, and because of that, there will never be any torque acting on the planet. Does that make a little bit more sense? Fantastic. So kind of going from that, at any point, we can always say that, okay, well, the angular momentum at any point should be conserved. This is essentially a point mass orbiting around something. So I'm going to take this point mass description of angular momentum, r cross p. Now, this angle, we're no longer dealing with a sine of 90 kind of deal here. We're going to call this sine of beta, where beta is the difference. So this is my r vector out to v. Whatever beta should be in any of these cases, this is what we can use to relate essentially where is it at in its orbit, where is it going around this thing, how far is it, what speed is it going at these points. We can use this conserved quantity, the angular momentum being conserved, along with our energy conservation to find all sorts of good information about what goes on with a planet. You only need a handful of details to really understand where else this thing is going to be. So, I want to try this out. Let's imagine the heavenly body formerly known as Pluto moves in a fairly elliptical orbit, right? It's somewhere between circular and elliptical, which I realize anything that is not circular but is still round is elliptical, but it's almost a circle. It's like not a super elliptical thing, but whatever. I'm getting kind of beyond the point at this point. Let's go ahead and say we have, at its closest approach to the sun, it is 4.45 times 10 to the 9th kilometers, and it's got a speed of 6.12 kilometers per second at that point. So that is a tangential speed. What is Pluto's speed at the aphelion, which is 7.3 times 10 to the 9th kilometers away? That is the farthest distance it ever gets from the sun, is 7.3 times 10 to the 9th kilometers. And at this point, we have decided Pluto's too small. They're going to be dismantling it, taking it out of the sky, unfortunately. But it had a good run while it lasted. But I'm going to say, take the next, say, 4 or so minutes. Come up with an answer for this one, and then let's see what you got. All right, so here's what we've got, right? We can go through this process ourselves right here, but what we're basically saying is that at any point throughout this entire rotation, wherever we would like to be, we can even draw out all these details. Let's imagine that we've got the full ellipse on this thing. Something like this, right? That's what the orbit looks like, where Pluto also goes off the rails. We've got a sun, we've got Pluto. At its nearest point, that angle beta, as we were talking about that thing, remember, so r would be pointing out like this, my velocity would be pointing something like this. That means that the angle right here is a right angle, makes it a little bit easier. Same deal right here. I've got my velocity going like this, I've got my r going like this. It is still a right angle this entire time. So when we're using that description, at either of these points, we could say that the angular momentum being r cross p, if we want to take an absolute value, because realistically I'm only concerned with quantities, I really don't care about the directions, r always points from the inner object to the outer object, from the axis of rotation out to our point, right? And that was true for all of our angular momentum stuff from chapter 12 as well, right? It always points from where that axis is. So the sun does not move that much. So the sun might as well be fixed in this case. So this is my axis of rotation. It's just a little bit strange because now we're not moving in a perfect circle anymore, right? That's where it's a little bit tricky. As it's going out like this, it's not necessarily a perfectly circular rotation, but that is still the axis of our rotation. So what we can say with this is for any of these quantities, we could say, all right, well then in this case, it is essentially just r, mv, sine, and in both cases here, the angle is 90 degrees. So I haven't specified whether I'm at my nearest or my farthest yet, because so far they have shared all of these quantities. So the mass of Pluto does not change between, the closest orbit and the farthest orbit. It is still at the same mass the entire time. So the only thing that actually matters here is going to be the radius away and its velocity at that point. Radius away and its velocity at that point, which is exactly what we are trying to say down at this bottom line right here. 2 points that we're particularly interested in are where these angles are 90, as easy as possible. So with all that in mind, really all what we need to do, we're looking for V final. Take this thing. I realize that I've drawn kind of a mess at this point, but this is essentially R naught over RF times V naught is equal to VF. I'm not even going to consider the order of magnitude. Screw it. Why would I? Right? Take R naught and let's just call that thing 4.45 divided by 7.30, because both of them have a 10 to the 9th anyways. Multiply that by 6.12, and what we should end up with is that our speed at that farthest point is something like 3.73 kilometers per second. So it does slow down quite a bit. Is the axis of rotation going out of the page? Yes, in that sense, that's the axis, as it would be pointing kind of through like that. Usually, I consider it as a point, mostly because a lot of the time you can have rotation in all 3 dimensions. So as it might be rotating around any of these points, I usually don't like to consider it like a rod poking through, but we could in this case. That would be all right. It's just got a stretchy string is what this is, right? So as it's kind of going out like that, as it goes a little bit further out, that string is, well, it's not pulling as much. That description doesn't work out very well. It's like a reverse spring. I don't know. Sprang, because we've already used sprung for something else. Yeah, it's a little bit strange in that one. I consider it to be a point, but you can consider it as a stick poking through. That would be totally fine. As for the in-class, no in-class today. I've only got this one question for you guys, so there's not a lot. But before anybody leaves, I am going to be talking about some of those details in the lab, and it would be very beneficial to hear these things. So, let's talk about a pretty important detail here. One of these details that I have mentioned in passing a couple times, and I said, hey, you need to know some details about some of these things. You might have to deal with something where you're taking an integral, and you need to understand what the function of mass would be. Today is the day that we need that. So here's what we've got. Most galaxies are not just point masses. They're clouds. Right? Galaxies, nebulae, they're all a bunch of different clouds, space dust, they form into things sometimes, but for the most part, even when I'm thinking about stars, how many stars are in this galaxy right here? Let's try and count. Have you given up yet? I'm not going to try and count these pixels, right? I might as well, even if I'm just looking at the stars, I might as well just call it dust at this point. It's not worth it to try and count every single individual mass at this point. More than 5 is a fantastic answer, because if it's more than 5, I'm not going to count it myself, right? I'm not going to deal with that. Instead, what I'm going to do is I'm going to say, okay, well, treat it like it's a big cloud. If it's a big cloud, then maybe we can work with something here, right? I see that, well, the middle is probably going to be pretty dense because we see something real bright going on there. But the rest of this, I could model it as essentially a big cloud of dust. There is a mass distribution as if this thing is just a big disk, right? I realize it's not solid like we're typically thinking about a disk, but it is still just a big disk of mass. Or in the case of a lot of different galaxies, we like to consider these as spheres because spheres are so much easier to deal with, right? We like circles and spheres when we get the chance to work with them, even if they're not super realistic. So here's what we have to consider. If we had a cloud of mass, how do we actually figure out what's going on with some of these things? How do we actually calculate out these values? Let's start there. There's going to be a quantity, and you have already dealt with this before, called a mass density. And a mass density, we typically symbolize it as rho. And the units of this are kilograms per cubic meter most of the time, right? You might change that, but it's mass over volume. That is to say, if I multiply my mass density by a volume, I get out mass. Now, there's this other very cool thing that when we're talking about how much gravitational force do you actually feel, I don't want to try to prove this one to you right now because there is a way that we go through with this, but here's what we would say. If I have a cloud, and let's say the total cloud is a capital R, I want to find how much gravitational force do I feel at this point. Right? Kind of like we do with Earth. When we're talking about Earth, we're talking about the radius of Earth. If you dig down 100 meters into the Earth, what kind of gravitational force do you feel then? Do you feel the same gravitational force? Let me take a concept check here. What do we think? Yes or no? No. Because now there's a lot of mass on the outside that is pulling me upwards in a sense. There's still some mass pulling me downwards, but there's a lot of it now pulling me upwards. And I'm not going to feel that same gravitational force as what I had felt on the surface. Beyond the fact that I'm closer to the center of mass, that's a contributing factor as well, but now there's not as much mass down beneath me, that's actually going to be contributing to that gravitational force. It turns out, mathematically, that this is equivalent to basically saying, all right, if I want to know what is my gravitational force at this particular point, somewhere within the mass distribution, what I need to consider is how much mass is contained inside of this bubble that I'm standing on. That bubble only. So what I'm going to do then is I would say if the total mass is m, the mass density of this cloud goes as capital M over the volume of the entire sphere. That is 4/3 pi capital R cubed. That's my mass density of this big cloud. I want to figure out how much mass do I have inside of my area. So let me call this mass in. Mass inside would be this mass density times however much volume I've got beneath me. So that is going to be 4/3 pi little r cubed. You'll see a 4/3 and a pi are going to cancel out. The mass, the effective mass, the mass that is inside the orbit that we are actually going to feel in our gravitational pull, is just going to be, essentially, mass n is equal little r cubed over big R cubed times the total mass. That is the ratio of how much mass is beneath us. And don't sleep on this one, because we're going to use it here for gravity, and then we're not going to need this kind of concept again for a little while. And then we're going to come back with the same idea in 192, and we're going to talk about charge density, where it's going to be essentially coulombs per cubic meter, and you're going to have to do this exact same thing, but dealing with charge rather than mass. Big mass, yes, capital M is the full dust, the full cloud. But once you have done that, now I would just say, okay, well, that's how much mass I have inside. Treat it like the same center mass we have as before. That M inside is right there in the middle. We are a distance, little r, away from this. And that's what we are going to use the two quantities for finding that gravitational force. Top right equation to the bottom right equation. M in, I would take this as my mass density times the volume inside. So that's, I'm plugging in rho into that equation. Rho goes right here. If rho goes right there, then that's what we would solve out for. Now, one other detail that I do want to highlight on this thing, because I see this mistake made a lot. You will need all of these, by the way, for the lab that you are working on here. These are all important details. Once I am a little bit farther out, let's look at our second point right here. How much mass is inside, and what is our distance away from that mass? Are we going to just take rho times 4/3 pi r cubed? I'm going to say, you better not. I'm not going to wait for an answer on that one. You better not do that. Because at this point, we are outside of the shape. The full cloud is beneath us at this point. This goes back to what's going on with our planetary model. We're outside of the shape at this point. We're no longer digging into the cloud or anything else like that. We no longer have to worry about how much of the mass of the cloud is beneath us. The whole cloud is beneath us. You should never see a mass quantity larger than the total mass of the cloud, which sounds a little bit ridiculous to say, but when you're just going through crunching the numbers, it's an easy mistake to make. So watch out for that one. Once you know you are outside of the cloud, once you are outside of that mass density, do not try to add any more mass to that. You are now outside, your equation changes. I'm not looking at what proportion of the mass I've got anymore because I've got the whole mass. I'm never going to have more than the whole mass. This is a pretty important detail because as you're working through this lab, you're going to consider two overlapping spheres. One of them is going to be our regular matter. The matter that we see, that we love, all of this good stuff. The other is what we will call dark matter. So, let me get into these details because this is kind of fun. This is one of the big problems that we're facing in physics right now. We have seen, for circular orbits, our full equation, our actual equation at this point, and let me move myself over a little bit so we can actually see that little, the subtitles that I've got down here. We have seen that if I am supposed to be dealing with any sort of orbital motion, circular motion, and we can look at this thing and we can say, hey, that looks kind of like a circle, right? I'd argue that that's circle-like, mostly, within a good order of approximation here. Okay, so then that should be G capital M over R. That capital M, that R right there is exactly what we just talked about right here. Right? How much capital M we've got is essentially how far in are we. In our case, looking at the solar system, capital M, the cloud, is our star, the sun. So as long as we are outside of the sun, the full mass that we're orbiting around is all just kind of contained right there. The full mass of the sun divided by how far away we are from it, multiply that by the gravitational constant, take a square root of the whole thing. It's a very long way to describe this equation that we've already seen. When we do that, we get a nice little looking graph just like this. And it's great. If we model all of our planets to it, it works very well. There's a little bit of discrepancy at a couple certain points, but it's usually not a detail to worry about. For the most part, these come in very good agreement with the equation that we have to predict them. So that's argument that, yeah, everything that we've learned so far, accurate. Perfect, right? The old laws of gravity and everything else, Newton, he wasn't wrong. Everything was fine. But here's where it gets a little bit more spicy. If we were to look at the Milky Way, the whole galaxy, a galactic scale, what we start to notice is that the orbital speed doesn't actually scale like what we expect it to. That is, we expected the orbital speed to make this shape right here, because that's what makes sense. But one of the things, if you have ever thought about, I know there's been a lot of graphics of what galaxies do as they spin. A lot of galaxies have these little arms, though. Now, with this argument, as we would expect this thing to go, this thing would be essentially doing some sort of mixing thing, right? Where this section, let me do this. Does my Stardust color work? Well, that's not very clear, I don't think. Let me do this in I'll do it in yellow. That should be visible. This section right here, right? I would expect that would mostly stay in place as if I'm following this arm, this part right here would probably be moving really, really fast and spin around, right? And I'd expect to see this kind of weird swirling motion, like a blender almost. But that's not what actually happens. What actually happens is that this entire shape is all spinning at the exact same rate, like you would expect a turntable to. If you took this picture right here, you slapped it onto an old vinyl, and you spun it around, that's how we actually see galaxies moving. But this equation says that shouldn't be the case. It shouldn't behave like this, because the fact that it does says that something with our mass is wrong. Something must be incorrect here, because otherwise this circular speed should be essentially trailing off as you go farther and farther away, as you get more and more outside of the dust cloud. So it is radically different, and we do see there's these little tiny curves essentially contained inside of here that do kind of follow this 1 over r thing that we expect pretty well. Not super well, but all right enough. But this weird nonsense is clearly not a regular function. And that's a big deal. That is almost even saying if you're starting to look very far out, some of the outside bits even actually move around the circle faster than the inside bits. So something is wrong, and that's really the answer here, right? That at a certain point, our understanding of gravity, something is incorrect. It works for people to planets. It works for planets to stars. It doesn't work from stars to galaxies. So, because they're spinning around faster, there's only a handful of explanations that we've got. One of them is that there's more matter there than we can actually see. See, as we have been doing this so far, we essentially calculate how much mass is supposed to be there based on how bright it is. And that's not an entirely unexpected thing. Most of the solar system's mass is often contained inside of the star, with some approximations. Even if we're modifying some of these quantities a little bit, we're taking a little bit of a rough guess for how much mass we expect to be there, but we're pretty sure in our guess. We have been looking at this for quite some time at this point, so it's not just a random kind of, pick a number from the dartboard and then guess with it. We have been spending quite a bit of time actually thinking about some of these quantities, and we've got a pretty solid answer for them. The problem is, even with all of that extra mass considered, it's not enough to actually recreate this graph. Even if we were to mess with the densities or anything else. Instead, what this is basically saying is that the mass is scaling at the exact same rate as the radius, which, if we go back to this equation right here, we don't expect to see that. The mass would have to scale essentially with this weird r cubed kind of shape to make this work. So one of the explanations is that there is more matter there distributed throughout that we can't actually see, known as dark matter. Dark matter doesn't interact with light. And because it doesn't interact with light, it could explain why we can't actually see it behaving in the galaxies. But if it does interact through gravity, then it explains why essentially the galaxies have this glue helping hold them together. The other explanation is that as we understand dynamics, Newton's original laws talking about force and mass and the gravitational equation are all just slightly incorrect. And by slightly incorrect, what I really mean here is that the acceleration, Newton's second law, F is equal to ma, is not quite spot on. It's a very close approximation, and for most things that we would see, it works very, very, very well. But for really, really, really small accelerations, there is this extra term. The actual term that we would expect to see looks something like this. And this is kind of a nasty looking equation, but what this is basically saying here is that anytime I am sufficiently small, this extra little term in here comes into play and it screws everything up just a little bit. So AN is the Newtonian acceleration. AO is essentially this little tiny extra term. And if A of n is 9.8 meters per second squared, A of O is much, 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 much smaller than that. It doesn't actually matter. But when we're talking galactic scale, the actual acceleration that they feel all the way out there is very, very tiny. This factor starts to come into play a little bit more. This is a theory known as MOND. And in a sense, they're competing theories. They have both seen a fair amount of evidence in support of them very recently. Dark matter, I think, is still the more popular theory of the two, because there is other evidence for dark matter, and there's a little bit of evidence for dark energy, which is kind of in a similar vein. But we think they are related in some way or another. Dark matter is kind of like a 70% think it's dark matter, 30% believe it's MOND, but both of them are essentially still waiting for more evidence to prove them one way or the other. So, your lab, your task with this lab, is to essentially take both of these equations, or both sets of theories, and compare them to show that you can use either theory to accurately replicate this graph. Now, in both cases, the reason that you can actually do that is because we have essentially made both of them to explain this graph. We have the evidence. We have come up with two competing theories to describe what we see in the evidence. So it is not definitive, it's not predicting or anything else like that quite yet. Even, this equation right here, this is essentially a what fits the graph very well. This fits the graph very well. So, we expect it to match. That's at the end of the day what we're expecting here. But I want you to essentially go through this thing, show that the actual galaxy, if we were treating it in the classical sense, does not match the data, and then use the two competing theories to show that these two do match the data much better than that, and how we actually calculate out some of those values. Also, sorry for skipping the question. Is physics 191 or 192 better? 192, hands down. Certainly. 192 is just cool. But it is a harder course, so, take it with a grain of salt on that one. But you're better at physics by that point, so, the level of difficulty kind of stays the same no matter what you're doing with these things, unfortunately. But you are getting much better at them, and we get to dive into some cooler concepts sometimes. So, that's all I've got. Kind of a short one today, but we wanted to space this out so you've got a little bit more time to dive through all of this material. Right, a little bit more time to work on the problems, a little bit more time to work on those labs. 192 is indeed offered next semester. There should be 2 sections at the exact same times as was this semester. But that's all I've got. Thanks for being here, team. I always appreciate it.